Hello everyone, my name is Andrew. My partner Phanidra and I will be providing a summary of a paper titled Memory Encryption, a Survey of Existing Techniques. It was written by Michael Henson and Stephen Taylor of Dartmouth College in 2014. The purpose of this paper is to provide a survey of solutions to the vulnerabilities presented by a lack of encryption in the upper layers of the memory hierarchy. The authors identify three main solution families. The first is hardware enhancements, which include modifications to current processor designs to enable encryption and decryption for memory accesses, as well as solutions which integrate into current architectures such as bus inserts. The second approach is operating system enhancements, which allow encryption and decryption to be handled in software. And the last solution family is identified as specialized industrial devices, which may use a combination of hardware and software, often in a non-standardized proprietary manner. For all these approaches, feasibility is determined with respect to ease of integration in existing designs, encryption overhead costs, and portability between designs. To provide some background, full disk encryption has emerged as a technique to provide confidentiality of data residing on disk, whether that is a hard disk, solid state, or external drives. However, the issue is that once data or code is loaded into main memory, it is unencrypted as it moves between main memory, the caches, and the processor. It is important to note that it is an assumption of memory encryption literature that the processor is included in the trusted computing base. Therefore, we are mainly interested in the chain from main memory up to the processor. Currently, with a volatile memory in this chain, vulnerabilities are short-lived in that unencrypted data is only accessible while power is applied, with state lost when power is removed. However, several alternative memory technologies such as magnetic RAM and ferroelectric RAM are being explored due to energy efficiency as well as tolerance of power failure. Should such non-volatile technologies become commonplace in the memory hierarchy, memory state will persist, enabling a greater attack window. Speaking of attacks, the threat model includes both hardware and software attacks with the assumption that attackers have physical access to the system, enabling invasive attacks such as bus probing. The operating system may be included or excluded from the trusted computing base. If it is excluded, it must be treated as an untrusted process, similar to any other process running on the processor. Primary goal of attackers is assumed to be stealing secrets such as data or keys themselves, as well as proprietary code being executed in the system. In general, encryption provides four basic protection properties: confidentiality, integrity, authentication, and non-repudiation. Of these, memory encryption is primarily concerned with runtime confidentiality. An important issue when discussing memory encryption is the speed gap that exists and continues to grow between the processor and memory. It is already on the critical path for performance, so additional overhead directly impacts user response time. Taking this into account, as well as the complexity of public key encryption, memory encryption literature primarily utilizes symmetric key crypto. Another important decision that must be made with memory encryption is the granularity of encryption. For instance, should all memory be encrypted with the same key? Or should it be encrypted at a per program or process level? Or perhaps the memory region and access pattern should be taken into account. For example, a runtime stack is accessed frequently, so encrypting or decrypting on every push or pop operation would add significant overhead. So Henson and Taylor identify several different forms of hardware enhancements. The first deals with modifications of current monolithic processors. A proposed architecture known as execute-only memory utilizes both public or asymmetric key as well as symmetric key crypto. Binary code is delivered to a chip using public key crypto, allowing the code to be encrypted for a particular system or chip. Symmetric keys within the binary segment memory into process-level compartments. And this architecture assumes a couple enhancements, including a private on-chip memory for storing the unique private key, as well as a symmetric key hardware unit. Runtime operation results in decrypting and encrypting when reading from and writing to memory, and it is often referred to as direct encryption. Another proposed technique, known as chip lock, looks to improve the security of direct encryption by storing a small trusted portion of the OS in a ROM. Known as trust code, this kernel code intercepts all memory access system calls and performs encryption without the knowledge of the untrusted portion of the OS. In both these methods, the one-way mapping of direct encryption may leak information about the original plaintext. So a one-time pad may be used to mitigate this weakness by using a random number to add a layer of confusion to the ciphertext. There is quite a bit of research regarding one-time pads, including generation of truly random numbers using counters and seeds, as well as minimizing the overhead of one-time pad generation on system performance. In multiprocessor systems, cache-to-cache communication must be protected in addition to the cache-to-memory path, which was the focus of monolithic processors. For symmetric multiprocessors, this is usually done using the shared system bus. But for distributed shared memory systems which do not have a physical shared bus, message passing must be used. Several methods have been proposed for cache-to-cache traffic protection. Cipher block chaining is one which encrypts each block with the result of the previous encrypted block, creating a chain. This implies sequential access, which is bad for the cache-to-memory path due to random access patterns. However, this is not as problematic for cache-to-cache traffic. Another method utilizes pad counters, for which there are a few different schemes. The most general method, termed private, each processor stores tables with send and receive counters for every other processor. This results in a really low overhead but large storage requirements, which obviously scales poorly as the number of processors is increased. In the shared scheme, only a single send counter is used, reducing storage requirements but increasing message overhead. And the last scheme, known as cached, it takes advantage of the fact that interprocessor communication is often performed in small groups. Therefore, a processor does not need to store counter information for all processors in the system, but just those with which it communicates. I will now turn it over to Phanindra to wrap up proposed hardware enhancements.
Thank you, Andrew. Hi, this is Phanindra. I'll be continuing the presentation from this point. So far, we have seen two kinds of hardware enhancement techniques. The third one discussed in the paper is bus inserts. These are the encryption units which are placed outside the CPU on the memory bus. Bus inserts are particularly important as they obviate the need to re-engineer commodity processors if at all an encryption unit has to be added. This is especially true in the case of legacy CPUs. SEC bus is one example offered. Its design is shown on the slide. It's a crypto coprocessor with storage and bus manager inside. We can also see several subblocks. For example, PSPE cache, that is the page security parameters entry cache, contains information used to map pages to corresponding security policy. Moreover, multiple encryption modes are possible to select depending on the kind of memory it is, like a code memory or data memory. Memory Encryption Control Unit, MECU, is another example presented. This is an OTP based technique and it attempts to obtain security on par with traditional RAMs using non-volatile memory. As mentioned earlier, using non-volatile memory offers several advantages. Even this is placed on memory bus. However, please note that placing the unit inside the RAM is also possible. Now let us see operating system based enhancements. Software based memory encryption techniques are particularly attractive as it is easy to add features without much change to hardware, just like in the case of bus insert encryption. Two examples are presented here. The first one proposed an OS controlled memory encryption for the systems which have software controllable cache locking. Intel Xscale series is an example of such a system. This approach has an interesting feature. Whenever a page fault occurs, a special handler moves the encrypted page into the chip boundary and decrypts there, finally placing into the cache and locking it. Unfortunately, this augmentation comes with a space overhead of 0.4%, so it is useful in systems which can trade off performance for a good protection. Crypt Keeper is another example where RAM is partitioned into two spaces, clear and crypt. As the name says, clear contains plain text, while crypt has encrypted version. Initially, the whole data is in clear, as in when the clear space is filled up, data is transferred to crypt. Which data to be transferred to crypt is based on an assumption that the number of frequently used pages is small, which is a fair assumption to make. Therefore, the least used pages will be encrypted and stored in the crypt. Let us now look into specialized industrial devices which are custom made for specific applications. For example, not all applications need very high processing speed. Dallas Semiconductor 5002FP is one such example. This is an 8051 compliant processor and operates at low frequency of 16 MHz. In addition to data, the processor encrypts memory addresses as well to prevent traffic analysis on the memory bus. Another interesting feature is that this uses spare processor cycles to place dummy memory accesses on the bus, as it is known that the analysis of memory access patterns can reveal useful information. The target applications for this device are ATMs and credit card terminals due to the low frequency of operation. IBM PCI series is another such example. It's a cryptographic coprocessor shown in the slide. This is much superior compared to the first example because it contains a tamper detection circuitry and it is designed to prevent all non-physical attacks. Consequently, the target applications include banking and finance systems. Apart from these, gaming systems offer another example of specialized devices. They are the most capable to incorporate memory encryption techniques because of very fast processing and huge space. For example, the Xbox 360 provides encrypted bootup, partially encrypted RAM, and an encrypted hypervisor. After touching upon various encryption techniques, a comparative analysis is presented. Despite non-existence of well-defined standards for comparison, this paper assumes several details to make a fair comparison. Parameters like execution and storage overhead, maturity level of test setup, and encryption algorithm used are considered. A system implemented on FPGA is considered to be very mature, whereas just a mathematical analysis is not so mature implementation. Most of the analysis are simulation based, which is somewhere between these two extremes. A technique called AEGIS, which is based on monolithic processor enhancements, came out to be offering best possible security. It is also the most matured implementation, that is, it is implemented on FPGA and it offers an execution overhead of 4.5%. So in short, this paper surveyed several encryption techniques and classified them into three categories: hardware-based, software-based enhancements, and specialized industrial devices. Further, the paper expresses concern on the absence of general-purpose commercial off-the-shelf solutions. However, the authors are optimistic about the growth that is happening in this domain. Next, if we observe the results, the overhead presented are in the range of 1% to 6,015%, which is a way too large number. This clearly points out the lack of proper standards for comparison. Also, the standard tools for simulation might ignore several implementation issues. However, recently several general purpose systems have been incorporating something called TPM chips for storing keys and encryption instructions, which can be used to validate the simulation results. With this, we conclude the presentation. Thank you very much for going through the whole content. Thanks a lot.